Hi all. This small lecture is about using continuity to find open and closed sets. So continuity can be used in many ways, but one of the big ways that it is helpful is that it gives short proofs that certain sets that you define are closed and open, or closed or open, and it is helpful because that way you don't have to do the tedious proofs that we did the first week of class. So how to use continuity to prove that sets are open and closed. And the crucial idea is that if you have, and the crucial way of applying this, before that we state the general statement, is that if you have a continuous real valued function, if you look at all the values which are between some strict values, so all the x's, such that f of x is between b and a, then this set is always open. You could prove this directly. We did this in lecture in a special case, but it will follow from this general principle. So for example, if you are in RD and you have the set where the sum of all the components is strictly less than D, and the sum of the squares is strictly less than 1, then this set is open. And why is that? Well, first of all, if we define the set of points where the first constraint is satisfied, that is all where the sum is less than 1, then this is the pre-image of an open interval, an unbounded open interval, under the function sum of xi. And this is continuous, so that is open. And then similarly, if we define B as being, and this shouldn't be called RD, this should be called omega. So B is all the x's such that sum of xi squared is less than 1. And then this is the pre-image under another function of the open interval 0 to 1. And actually that's always non-negative, so we don't even have to take the full thing. But what is g? G of x now is the continuous function xi squared, summing over the components. And you could also recognize this as the unit ball if you wanted, but omega is A intersected B, and each is open. So omega is open. Much easier than actually trying to figure out for every point that satisfies these two constraints what delta would, or what radius would work. It's good to still have that in your toolbox because sometimes that is just the easiest way to do things, but this is much more streamlined and it's better, it's more efficient, especially for more complex sets. So what is this based on? This is based on actually an equivalent statement that if f is epsilon delta continuous, this is if and only if the pre-images of open sets are open, and also if and only if the pre-images of closed sets are closed. And this is often used just like in the examples that we had before. So one remark here, this definition, the second definition here, is often used in topology 121. So you may see that there. And this is the way that actually you see that these statements are equivalent to each other. Now, if we want to prove such a thing, then we should show that these are equivalent. Well, how we will do this, we will show that 1 implies 3, 3 implies 4, and then 4 implies 1. And I'm using the numbering here from the original lecture. So the 2 condition was the sequential continuity. Actually, that 2 is used in this last implication. So 1 implies 3. That's probably the most important one to understand. Okay. So let's set things up. Assume that 1 is true. So F is delta epsilon continuous, or epsilon delta continuous. I guess I usually put the letters differently. And assume in setting up the proof for 3 that O subset of the image set is open. We want to show that F pre-image of O subset of X is open as well. Now this subset of X is superfluous here. It's just to emphasize that to the reader and to ourselves that we're working now on the X side. So let's pick X in the pre-image of O. That is, and we'll immediately write it in a way that will be useful in the proof. So fx is equal to y is in O. And what do we have to do? We have to verify the condition of openness, so find some radius. Well, the idea is that we first find the radius on the image side and then use the epsilon delta continuity to go on the domain side. So since this is on the image side, since O is open and Y is in O, then there exists some R positive such that BYR, and this is a ball in Y, is contained in O. Okay, so let's now flip it to the domain side. And let's write this in a way that will be useful for us. So if Z to Y is less than R, then that means that Z is in O. Now let's go to the domain side. Well, use epsilon equal to R, then there exists a delta positive such that if distance W to X, and we have to use a different letter, is less than delta, then distance of f of W to f of X is less than or equal to, and let's use R over 2 here, less than or equal to R over 2, because in our definition we had less than or equal to, which is strictly less than R. So let's, and okay, so with this choice, we have to combine these two implications. If W is in Bx delta, then that means that distance W to X is at most delta. This means, by what we just said, that distance of f of W to f of X is strictly less than R. But what that means is that if we use f of W is equal to Z, that f of W, and we know that f of X is equal to Y, that f of W is actually in O. But this means that this whole statement here is the same thing as saying that Bx delta, any point in Bx delta is mapped to a point in O, meaning that the points are in the pre-image of O, and we found our desired ball. So the pre-image is open. Okay, 1 implies 2 is shown. Next, 2 implies 3. So we know that open sets, their pre-images are open. Let's apply it to go to closed sets. And this is done with the usual trick of using complements. So we know that for all open sets, assume 2, and I won't write it again now. You'll have these notes, you can look at them. So assuming 2, let's fix, and we want to prove 3, so let's fix a closed set, F subset of Y. So we want to show that the pre-image of that is closed. Well, and we want to use 2, so let's define O equals F's complement, which is now open. And then we know by 2 that F inverse of O is open. But now F inverse, let's call this V, F inverse of F is equal to the complement of F inverse of O. And this you can verify by definition of functions, definitions of pre-images. So it's V equal to V complement. This is a good basic exercise to check that this is true. But now V is open, as V is open, then we know that the complement V is closed. So F inverse of F is closed. And we're done. So it's the usual trick of going to the complement. So the last part of this proof of classifying continuity using open and closed sets is about proving that 3, that is the pre-image of every closed set is open, implies the epsilon delta definition. In this case, the proof is by contradiction. That is, means that we assume that 3 holds, but that 1 fails. So for what it means for the epsilon delta the condition to fail, we saw this earlier with the sequential continuity, is that there exists a point, there exists a epsilon such that no matter how close you get, so that is for every epsilon, there exists a point that is very close and the images are very far. This is how you contradict an implication. The assumption is true, but the conclusion is false. Well, based on this, we want to apply contradict 3. So you could also construct this as a proof proof by contrapositive if you wanted. But let's define a set F. This is on the image side and consists of all the points whose distance is at most epsilon from the image point of f of x. Now, this is a closed set. And one way of seeing it is because its complement is actually all the points within distance epsilon, which is open, as we've seen before. So F is closed, so its pre-image is also closed by 3. The pre-image of every closed set should be closed. And we know that X is not in F inverse, because the distance of f of x to f of x is equal to 0. Well, how do you use this? Now, F inverse is closed, and X is in the complement. And the complement of a closed set is open, as we've seen. That means that there exists a delta. There's no coincidence that I'm using the same delta as above, because it will play the same role, and it will choose delta to be the same value. That if I take a ball of radius that delta intersected with that pre-image, that this is empty. This means to lie in the complement of a closed set, which is open. But by assumption, there also exists a y that is very close within delta over 2, which is strictly less than delta. And why we have to use delta over 2 is we want strictly less, but so that the image of that point is far away. But okay, the image point is far away. That means that Fy is in F. In other words, y is in F inverse of F. So y is a point of F inverse of F. However, also, distance from x to y by construction is strictly less than delta. So y is a point of Bx delta, which means that so now y is in the preimage of F and it is in the Bx delta, so it's in both of these sets. But this is a contradiction. Why? Because we just said before this claim that the intersection is empty, yet we found a point inside there. Contradiction. So our assumption must have been false, and 1 must have been true. Proof by contradiction is complete.